Hello everyone, thank you for your interest in this topic. The video that you're about to see was taken from my Differential Equations class at Amarillo College. We had a guest speaker, Mr. Collin Witherspoon, who is the Executive Director of Decision Analytics and IR or Institutional Research at Amarillo College. Previously, he was chair for the Department of Mathematics, and before that he was an instructor of mathematics, often teaching differential equations. He has taken his knowledge and used it to construct a model of the spread of COVID-19 in the Amarillo area, or the surface area of Amarillo College. That's about a 60-mile radius around Amarillo, Texas. He has constructed a system of nonlinear differential equations, which he solves with numerical processes, and he updates his model every day with data from the Johns Hopkins Research information, and he has used it to predict the spread of the virus in our community. His model is very fascinating, and I know that you will be blessed by what you hear. So again, thank you for your interest in this video.
And take the floor.
Okay. Well, good morning, everyone. So like Ms. Cornell said, I did teach DE for several years. Actually, that was you can't really have a specialty going for your master's degree, but that was basically the specialty while I was pursuing my master's degree. I did a lot of things in differential equations and modeling things with differential equations and so on and so forth. So what I'm going to do is I'm going to show you the basic model, show you how you create this model, and then from there, depending on time, so that may require some of you to say, you have to get off or not, because getting into what it looks like in our area, okay, requires a little bit more time. Okay, but I'm going to present my screen now. So can everyone see this?
Yes, sir.
Yes, okay. So we're going to get into modeling the spread of infectious diseases and start talking about the basic model. And this is a basic model that everyone trying to model it right now is using. And it's the most common model. Okay, so the model itself is called the SIR model. Okay, and like I said, they're the most common models used for showing how a disease or how an infectious disease spreads through a community or a population. The model's name is basically an acronym formed by the dependent variables of the model. Okay, so S is the number of susceptible people in the population at time t. The I is the number of infected people at time t, and R is the number of recovered people at time t. So SIR, a SIR model. Okay. So the basis of SIR models is what's called compartmental analysis. I don't know how much modeling you all have done in differential equations at this point, but this is a common way to model things, is through a compartmental analysis, which basically looks at a process as a system where you have interacting compartments, but they're distinct in the sense that if you're in one compartment, you can't be in the other compartment. Okay, so such systems are visualized as block diagrams. So this is a block diagram for the SIR model. Okay, susceptible moves to infected, infected moves to recovered. Now there are other models that build on this. For instance, there could be a SIRS, an SIRS, that is, after you recover, you become susceptible again, and it pushes you back to the susceptible compartment. Okay, but this is a basic SIR model, and until you know whether that is the case, whether people can move back to the susceptible compartment or not, you wouldn't model it that way. Okay, so some assumptions and parameters to actually build this model. Okay, so the gain in the infected compartment, and thus the loss from the susceptible compartment, is assumed to be at a rate proportional to the number of infectives and susceptibles, or B times SI, where B is some value greater than 0. Okay, so that indicates a proportionality between S and I, okay? So one way to interpret that B parameter is it's the probability that an infected person will encounter or run into a susceptible person and infect them. So it's like a probability, okay, argument or parameter, okay? So that's the B. The rate of removal from the infected compartment to the recovered compartment is assumed to be proportional to the number of infectives, Ki, right? The number of people that are infected, some proportion of them will move out of the infected compartment into the recovered compartment, okay? And K needs to be greater than 0. 1 over K is a measure of the time spent inside the infected compartment. All right, so basically if it's in days, and then 1 over K is the number of days you are infected. All right, so to talk about these in terms of modeling an actual pandemic going on, K is something you can know relatively soon. That is, you watch people that are infected and you find out how many days does it take that person to no longer be infected. B is much more complicated, okay? Because to determine that probability, in fact, you have to wait until the whole pandemic is done. Then you can actually calculate the B value. So you have to come up with a way to approximate or make an assumption on what that B value should be. And I'll talk to you about how I do that for our area, okay, when it comes to the coronavirus. So like I said, K can be known relatively soon, okay, because that's just watching how long it takes infected people to get over the infection, okay. B is more complicated. All right, so based on these assumptions, these parameters and what they mean, bear in mind it says the gain, the infected compartment, and thus the loss from the susceptible compartment is that BSI, okay? So the model, how do we model this in a set of differential equations? We say, okay, so the rated change of the susceptible compartment with respect to time is the negative of that proportionality times the susceptible times infected, okay? The reason it's negative is, yes, susceptible people are becoming infected. You should be always pulling people out of the susceptible compartment, okay? So negative BSI is how we model that movement out of susceptible. Okay. Then dI/dt, the rate of change of I with respect to time, right? Well, moving out of the susceptible, the BSI is moving into the infected at the same rate, okay? And then they are recovering. So we've got an addition to the infective compartment from that BSI, but then we're removing them at a rate K times I, okay? So again, think of these as rates of change. So these are rate values, right? They're telling you how it's changing. So far, so good, right? The susceptible, the change in susceptible should be negative always, right? That rate of change should be negative, indicating a decreasing value, right? Because that's what the derivative is telling you, right? It's decreasing through time, all right? Then you got those infecteds. That's all the people coming out of the susceptible compartment minus the people recovering, all right? And then you got the recovery, which is basically just that Ki, right? Those that are no longer infected at that rate K times I, all right? So that is the model, okay? That is the system of differential equations. But what we need at this point would be a set of initial conditions, right? To create an actual initial value problem where we get actual solutions coming out of this that have values to them. Some initial conditions, right? So S of 0 equaling S naught greater than 0, I of 0 equaling I naught also greater than 0, and R of 0 equaling 0. So some notes on that, right? So the initial susceptibles, S naught, would be the entire population unless there is a set of people that are immune already. They have immunity. Then you would have to, right, set that S naught less than the full population, okay? I naught must start with the value greater than 0. Otherwise, there are no infected people in the population and you would have no spread of the disease. And R naught should be 0 because when you initially start, no one's recovered. So with the system, right, of differential equations and these initial conditions, we get the SIR initial value problem. So I'll give you a second just to scan over that really quick.
Can I introduce one thing here? The way you have this set up with compartments looks a lot like the Riki Roko. My students will know what that is. When we're looking at fluid flow from one tank to another, where we look at the
it's
rate.
exactly like that. Yeah.
Right.
It's the same thing. Yeah.
Yeah.
So the Riki Roko is actually a compartmental analysis. It's the same thing. A lot of differential equation models are based on compartmental analysis. Flow from one to another. And so that's a very general idea, right? So flow from a tank, one tank to another tank. Flow of heat from one area to another area. Okay, flow of susceptible people to infected people. A lot of DE models are based on that compartmental analysis idea. So you're absolutely right. So you can really think of it like that. These are 3 tanks, right? You're flowing out of susceptible to infected. You're flowing out of infected to recover at certain rates.
Right. I think that will really register with them because we've looked at that a lot this semester.
Yeah, that was gold.
Yeah, so just like, you can basically look at anything like this, right? Anything that looks like that block. And that's a very general idea on how to model things, okay? Now, remember, like I said, you could have a SIRS, a SIRS. So you could think of 3 tanks attached to each other, and that last tank is flowing back into the first, right? And you get that flow, okay? Which sometimes that happens because the last tank creates some kind, if it's a chemical process, you can end up with autocatalytic state at that point, and that is what you were trying to get to, and you want that to flow back into the original tank to keep getting that autocatalytic reaction going on. So it's a model for a lot of things. Okay, so solving the SIR initial value problem, like how would we go about solving this thing? Okay, so at this point we have an IVP, right? And from theory, I'm not sure how much theory you all covered in the system of differential equations. Knowing Miss Cornell, she definitely touched on it, right? And if we've got this system, how do we know there's a solution? Okay, so from theory, we know it has a solution in some rectangular region containing the initial value point, okay? And that just comes straight from theory based on the system itself, okay? This system, each of these different differential equations itself is continuous, so we don't have any issues. It will have a solution in this case, I call it rectangular, but think about it, it's 4-dimensional, so it's not really an actual rectangle in the plane, okay? But we still call it a rectangular region, okay? But note the DE is definitely nonlinear, okay? It's nonlinear because you have that SI value in there, right? That product of 2 of the dependent variables, which forces it to be a nonlinear a system of differential equations, okay? So none of the methods that you've perhaps done at this point, you wouldn't be able to use those to solve this system of differential equations. And as in many cases with nonlinear differential equations, it is not possible to even find an explicit or what's called an analytic solution to the system, okay? You know there is a solution. That's what theory gives you, okay? So you definitely know there is a solution, but you don't know how to get to that analytic solution or explicit solution. So what I'm going to show you is one method of doing that, which is called Euler's method. This is a numerical method for solving or approximately solving a system of differential equations, or just a single differential equation. So Euler's method. What Euler's method uses is the tangent line, okay, to obtain approximations. All right. So I'm going to start with a simple one so you get the idea instead of complicating it with having a system at this point. So we're going to start with a simple initial value problem consisting of one unknown function, okay? So we're just going to have that function be y, initial value being y at t naught equals y naught, okay? So we want to find a numerical approximation for y, and you'll understand what that means in a few minutes, okay? So remember, like I said, Euler's method uses tangent line. So the slope of the tangent line at t naught y naught is the derivative at that point, right? Remember, f is designating the derivative here for simplicity, right? So the slope is the derivative at that point. So the tangent line to y at that point is given by that equation, right? So that is simply the point slope form of the equation of a line solved for y, right? Y minus y naught equals slope. Remember, that's what the derivative is giving me, the slope at a point. The slope times t minus t naught, and then solve for y. Okay? So that is the tangent line at that point. Okay? So what we want to do is we want to grab a set of t values, a set of time values. Okay, we basically want to partition a time interval and get a set of t values to approximate y at. Okay, and we can follow the tangent line at each point to get the value of y at the next point. Okay, to simplify it, we're going to choose the set of time values so that delta t, the difference in the time values, right? Delta t being t sub j plus 1 minus t sub j, we want to choose it to be constant. All right? So we basically want the distance between, okay, the distance between the time values to be constant. Okay? If we're at that point, then what I've done in this first equation is I have substituted y sub 1 as my approximation for y sub 1 will be y naught plus the derivative or the slope at that point times t1 minus t naught. So I basically use this equation, right? Y minus y naught plus slope times t minus t naught, but I've used it to approximate y sub 1. Okay? And y sub 1 should be the value of y at t sub 1. Okay? Then I simplify that to use my delta t. Then y sub 2, well, I'm going to have it be y sub 1 plus the derivative at t1 y1 times that also delta t. So I'm approximating my y for each of those time values, right? y1 corresponds to t1, y2 is y at t2, y sub j plus 1 is going to be obtained by taking the previous y plus the slope at that previous time point times the difference in the time values, the delta t. So this is what you do. It's just an iteration. You start with your initial condition, which you know, right? Y naught, t naught. You know that initial condition, okay? You plug that in to get y1, and then you move forward, right? You get y1, t1, y1, t2, y2, t3, y3, so on and so forth, all the way to the very end where you've got your y sub n and t sub n values. Okay, so numerical solution of the SIR initial value problem. Okay, so I just pulled that back in so you can see that. Okay, so an approximate numerical solution will basically consist of a set of points. It will just be a set of points where I have approximated the system at each time value t sub j. So I've got this set of, four-dimensional points, tj, sj, I sub j, r sub j, for all of my time values, given by, and note what I've done, right? S sub j plus 1 is S sub j plus derivative. All right, go up there. Negative b si is the derivative. I'm plugging that in. Negative b sj ij times my delta t. Then my I sub j plus 1 would be my I sub j plus the derivative, okay, times delta t. R sub j plus 1 is R sub j plus the derivative times delta t. All right? So it is just using that last equation there, okay, to say how I'm going to get the numerical approximation for the system. Okay? So that is Euler's method. That's called Euler's method. There's lots of different methods, okay? And there's Runge-Kutta methods. There's what are called finite mesh methods. There's all sorts of methods for approximating differential equations and systems using numerical processes. Euler's method is one of the simplest, and depending on what you think the curve looks like, it can be extremely accurate, okay, in your approximations, as accurate as what's called the fourth order Runge-Kutta method, which is the most commonly used method in numerical processes. But it can be extremely accurate, especially if you use your delta t, if you keep it pretty small, okay? And it's one of the simplest methods to implement, okay? But we could use any method we want, really, okay? Okay, so here's an example. All right, here's an example. So what I've got here at the top, so I wrote a computer program, right? So this is the idea, right? Write a computer program, you create it in such a way that you can solve this system of differential equations numerically using some numerical method like Euler's method, okay? So I output my parameters, the parameters I use to run this model, okay? So S naught, and you'll see where those values come from in just a minute. But S naught, just think of it. I chose a value. Note that S naught and N are the same value. N's my total population. So S naught is the total population. I'm assuming no immunity by any group in this population. I naught, let's say 10. You always have to have some number that are infected. And you would never know exactly how many unless you could trace them all the way back, okay, to the time point, and you had tested everyone in the population already. All right, you would never know exactly how many people were infected originally. R naught, like I said, there are no recovereds initially. I chose a B value. Remember, the B value is that probability that an infected person would run into a susceptible person and get them infected, okay? I chose 0.5, so think about that. You have a 50-50 chance of an infected person running into a susceptible person and getting them infected. That's pretty high. Okay, that's a pretty high probability. All right, K equals 0.07. Remember, this is 1 over K is basically number of days the person is infected, okay, and contagious. Delta T, I chose 0.1. And then you got to know how far out you're going to run it. I run it out to T final 150. So think of this as days. I ran it from first day being the 0th day out to 150 days. Okay. And that graph, note what I did. I basically adjusted the model so that I was getting percent of population instead of the population numbers themselves. So I adjusted the model to make it simpler, okay, because it's easier to see what it looks like in terms of percent of the population. It gives you a better idea about what's going on, okay? All right, so you look at it, right? The blue graph just being the susceptibles, the red one being the infectives, or infected people, and the R being the recovered. All right, you initially start 100% of the population is infected, 0% of the population is recovered, and the infected, you know, at 10 with that size population, that's pretty small. Okay, that's pretty small. But look at what happens, right? So it doesn't take a really long time for this thing to basically turn into exponential growth in the infected. All right, and you can see that this is basically exponential growth, and you can see that if you took the log of that infected value. All right, it would basically follow a straight line if you took the natural log of it, okay, through time. So it's just exponential there, and you get that significant drop in susceptibles, and then finally your recovereds kick in, and people start recovering. But no, even at the peak, you're still infecting people. Even after that point, you're still getting more susceptibles infected. But note that with this type of probability, this type of B value being that high, you basically run and you get every person infected through time. Okay? It basically becomes 0 susceptible. They're all infected and 100% recovery. Now, the thing to keep in mind about recovery, as a compartment and as a general idea in a SIR model, okay, recovery is two things in reality. It is you actually recovered or you died. Okay, so both are included in that in a basic SIR model. Okay, so that's that. And then you can see the first 10 days. So this is just the output of this model for the first 10 days. Right? So you can see how fast that's happening, right? You can see how fast that infected is growing. And that's because the B value is at 0.5. That's a huge B value, okay? That's at 50. It's a 50-50 chance an infected person will run into a susceptible person and infect them. Okay? So if you understand that basic model, okay, then let me pause for a second and ask, are there any questions? Anyone have any questions over anything?
I would like to know, how did you come up with your B value? Is that based on the news, or you're just making a wild guess there?
Okay, well, remember, right now I'm just showing you the model. This is not actual to our area. This is not actual to the coronavirus, all right? So I'm going to move to that. I just need you to understand where everything comes from and give you a sense of what the model output looks like.
Okay.
Are you with me?
Yes. And the
Yes.
the SIRS model with the S on the end.
Mm-hmm.
So would that apply to those who have been infected and recover and then get reinfected?
That's right.
Okay. Okay.
Yep. So if, for instance, the common flu, right?
Mm-hmm.
It's not so common, but it's common because it spreads throughout the world pretty quickly. But we have a vaccine, obviously. So the common flu is known over the past 2 years, the current strains are reinfecting people. So people are recovering and then they're getting reinfected in the flu season. So we do know that there are definitely viruses that your antibody buildup doesn't give you long-term immunity. Now there are others like the SARS, and which was SARS COVID-19, okay, that they seem to think you get about 2 years of immunity if you were infected, but we don't know about the coronavirus yet. Okay? So you just assume that it's not going to happen and you move forward with the model, okay, until you know for sure. And then you would have to incorporate that if you were going to use that model to try to predict, okay. Okay, so comparing some B values so that you can see what happens as you change B, okay? So that red is that 0.5 I chose, right? The green's 0.3 and the blue's 0.2. This is what they mean when they say flatten the curve, okay? Note what it's doing. One, it's reducing the peak infection. That is, on the day that you have peak infection, the B value determines how high that will be on that day. So one, it reduces that, but it reduces that by spreading it out, okay? It elongates your curve through time, creating a much reduced B value, for instance, at 0.2, okay? Right? Somewhere between 20 and 30%, closer to 30, it's probably about 28% infected, right? But look, it stretched out the time it takes to get to that peak. All right. So this is what they mean by flattening the curve. Remember, if you do things like social distancing and everything, you're going to flatten it, but the virus is going to hang out longer because you'll still have the population that is susceptible, and you're still going to have those infected individuals for so many days. And unless you go on absolute lockdown, that is, no one leaves from where they currently are, period, you're going to still have the spread of the disease. It's just going to make it less at that peak date. And for the coronavirus, the concern with any outbreak of a virus is that that peak day will overwhelm your medical facilities, and people will die simply because they cannot be treated. So the point of trying to flatten the curve is to make it where you can sustain that peak in your medical facilities. It's not that we want the virus to hang out longer. It's that we don't want as many people to die because they can't be treated for it. Okay, so that's the key. Okay, so if we want to look at how I did this to, so what I did is I modeled this for different regions. So modeling the spread of the coronavirus in AC service region, okay, because that's specific to Amarillo College, all right? So SIR model and approximating B, right? How do you decide what that B value is going to be when a pandemic is actually in process, okay? Okay, so may want to increase this a little bit so you can see it. Can everyone see the screen? Good? Okay.
Yes, we're good.
Okay. So the following analysis, basically, we want to look at the impact COVID-19 may have on AC by basically looking at how the virus will possibly spread through the AC service region. Now, that region consists of those counties that I've listed, okay? Those 9 counties consist of what is called the AC service region. It is nearly a 60-mile radius from the center of Amarillo, okay? But it's kind of skewed toward the west, all right, to stay away from 2 other colleges' service areas, which is Frank Phillips and Clarendon, okay? So it's a little interesting. It's about a 60-mile radius around the center of Amarillo, okay? Okay, so note that the population of this region is about 330,000 people, okay? And 78% of that population resides in 2 counties, Potter and Randall. 78% of those people basically reside in Amarillo and Canyon, all right? So the following data that I show shows the history of the spread in the AC service region, okay? This data, I obtained this data, so I write a lot of programs also, so a lot of computer science involved in this also at the same time. So I wrote code and everything, and we implemented a way to every morning automatically pull the data from the Johns Hopkins Coronavirus Resource Center. We pull the data down every morning, and we load it into what we call our IR data warehouse. And then we can generate this every morning, okay, automatically. All right? So we did that. So this is coming straight from that Johns Hopkins Coronavirus Resource Center, which is being used to track the spread of the virus through, well, basically the world. So they have data from all over the world, okay? So we started out, right, we're moving along. Well, in the AC service region, here's our new cases, all right? Yesterday, this is 2 days ago. This is May 3rd. I haven't updated it this morning yet because usually I run it in the morning, but I decided to spend my time with you all this morning, okay? So I haven't run it for this morning, so this is as of May 3rd, okay? But you can see that on May 3rd, we had our 2nd highest day ever of new cases. New cases, all right? So we are definitely we are just now starting to hit the exponential part of an infectious disease outbreak. We are just now hitting where we're going to see significant increases in the number of people infected each day, okay? Here are new deaths, and this is how you can tell. This is the natural log of confirmed cases. When the natural log of something basically lines up on a line, you know it's exponential. All right? Because that's what taking the logarithm of an exponential gives you. It gives you a line. Okay? Okay, so here's what it looks like if you want to look at the actual numbers, right? So this is just last 14 days, right? And these are just confirmed. Remember, those that have been tested and known to have it. Okay? New cases, new deaths, and this CFR is what's called the case fatality rate. and it is the number of people that have died divided by the number of people that have been confirmed to have it. Okay. Okay, so what I do is I create 3 scenarios to try to estimate what B will be, okay, what that B parameter will be. So note that one way to interpret B, another way to interpret it is as a social distancing parameter. Okay, so think about it. B is the probability that an infected person will run into a susceptible person and infect them. If you have social distancing policies in place, that probability should start to drop because it should be much less probable that people are running into each other. All right. So what I do is I get a best case scenario, and it is based on a SIR model with B equaling 0.18. And the way I do that, so this is other, okay, mathematical processes, and this is finding the best fit off of a sum of squared error value. Okay, so you take your model, the actual SIR model, which is in red in this graph, and you basically take the difference between it and the actual confirmed cases, you sum up their difference of squares, and you take the square root, and you find the smallest one. All right, and you can see that B, the green is the actual confirmed cases, and the red is the SIR model with that B value in it. This is looking at it on a log scale. Okay. And so we see that the model with that B value says that there's 1,515 people versus 1,508. But now note, that is the best case scenario because that is based on confirmed cases, which is based on the number of tests you're doing, right? Fewer tests, less knowledge. So the following data shows this model along with peak infection data, right? So I run that model all the way out, right? This is what it shows for the next 10 days based on best case scenario. Infected right now, 1,500. In 10 days, 3,900. Over 3 times that amount, best case scenario. It pushes that infected peak infection day out to June 25th. With 80,000 people infected, okay? And note that that's 99 days. Right now, we're at 46 days. We're right in this early stage of that graph, guys, but it's still growing quick. And that peaks 99 days. Okay, so that's the best case scenario. Now, we know we're not there because we haven't tested anywhere near enough. The city of Amarillo has tested about 1.9% of its population. The state of Texas, about 1.5% of the population. So we know there are more infected people. And we do know by the spread of the virus that there are infected people that show no signs whatsoever. And they infect other people. So we know that's best case. That's best case, right? So then I choose a worst case. And it's based on probability. Okay? So worst case. And I state all that, right? Given the limited number of tests that have been performed in this region, 1.94% of the population as of May 3rd, we should definitely assume that there are significantly more people infected than that, okay? And I use a probabilistic argument to come up with how many people you would think are infected just based on probability, okay? So note what I do here, a little math here with some probability, right? Okay, so let N be the number of people in the population, A be the set of all people in the population that have been tested, and B be the set of all people in the population that have been infected. So we know explicitly what the probability of A is. You take total number of people tested and divide by the population. That's the probability of the set of people who have been tested in the population. So I know the probability of the number of people that have not been tested, right? Which is called the probability of its complement, A prime, which is 1 minus the probability of A. Okay, so the probability that you haven't been tested, right? Probability that you haven't been tested. The probability that you've been tested and have COVID-19. So that's a conditional probability. That's the probability of B given A. The probability that you've got COVID-19 and you've been given that you've been tested. We know that because we know how many have been tested and we know how many out of those tested have been confirmed to have it. So we know that probability. So how do you get an estimate? Well, so the number of people infected, worst case scenario would be the probability of people that are infected given that they've been tested times the probability of haven't been tested times the total population. That's worst case scenario. As of May 3rd, 52,000 people. Okay, so you use that, you run your SIR model. This is SIR model would be at, I found the model that comes closest to 52,329 on that day, right? On the day. So I found the model that comes closest just to that value on a single day. And I use that model for worst case. So this worst case scenario, the worst case scenario would say that we got 51,000 people infected as of May 3rd, and we will be at 116,000 in 10 days. And that will happen on May 17th. Well, we know we're not there. We also know we're not at the worst case. There's no way we're at the worst case either. Okay? So what's the most likely scenario? So now it comes like a squeeze. You're basically using a squeeze. You got best case, you got worst case. What's the most likely? It's somewhere in between. You could choose any value you want in between. I'd simply choose the midpoint between the best B and the worst B. And there is the most likely scenario, okay, for that B. That's the model. It says today, or on May 3rd, instead of 1,500, we're at 9,800. And yes, just like the other, in the next 10 days, we will more than triple the number of infected people. In the next 10 days, and that's still 55 days out. That's just right. Look at that graph. You can estimate where 55 is. T equals 55. We look at a peak infection on May 31st of about 106,000 people, or 107,000. And I use other data to project out the number of people that would need to be hospitalized, not necessarily that they will be hospitalized. Okay. So that is the most likely scenario, right? Somewhere in between best, which is an exact fit to confirmed cases, and worst, which is that probability argument, okay? Somewhere in between. And again, this would change every day. As you get more tests, it could change not just the best case scenario, but it will also change the worst case scenario. So through time, these two should start getting closer and closer to each other. And you'll be able to get the most likely case more and more accurate. So you could use this model right now, right? With that B at 0.2225, the midpoint between best and worst, as the thing to use to project what's going to be happening. And you could run this out as many days as you want, right? I mean, it's a model. I just chose to display the next 10 days. All right. And here you can see the scenario comparisons. And then, because I had shown this to other people, I gave them the model, right? And how it went to understand where that B is and K is coming from. Okay. So yes, I would say that this is the most likely scenario. This will be updated today again, but I would say it's getting closer. Basically, this value is starting to change less and less as I've been running it each day. All right. So we're starting to narrow in on, yes, this is getting closer and closer to the most likely. So any questions?
So this model is updated on a daily basis, and this is specifically for our region. So we are very privileged to be able to hear your results because, again, it is very local and very personal. And one interesting thing is if we are on the point where it's taking off exponentially and our shelter at home in place has been revoked, do you anticipate
we have problems
changing your model?
Yes, we have problems. So the problem is going to be this. What I believe is going to happen within the next few days is that the best case, because 2 days ago, the best case for AC service region was 0.17. So this is just going to start ticking up. So as you loosen social distancing parameters, you increase the probability that an infected person is going to run into a susceptible person. So the B will start to go up. So yes, that is a problem. And that will push the most likely scenario, but it's going to push the B closer to the worst case.
Mm-hmm.
So the testing in our region hasn't been the most productive, or around the country in general. I mean, if you really think about it, if you think about it on a mathematical basis, an epidemiological basis, those new projections that the University of Washington is putting out, that people have been using to project the number of deaths and hospitalizations, if you read that, they don't show the exact model, but they show the parameters. And the parameters they use for the previous projections had to do with these things, these social distancing parameters being in place. And as you remove those, their model shows a much higher death rate because their original model showed a band, this translucent band around their current projection. And it had very high values. And that was indicating what happens if you start removing those social distancing parameters. If you allow schools to go back into session and meet in person, if you allow this and allow that and all these things. So absolutely, I suspect over the next week, we will see this B value best case B value will start to go up. And that will push the most likely scenario up.
Right. And then over time, as the people move from the middle category of infected to recovered, and things go back to normal, that's when they begin talking about the second wave of the virus hitting, and then we start this model all over again.
Absolutely.
And do you anticipate
But
with this?
if we come to the point where we know the pandemic, and that problem is we're just not going to know that the pandemic is over totally. It's most likely now endemic. It's in the human population, and it will continue to spread most likely, and it will start to mutate. So most likely it's just going to continue to spread around the world, and then it will just hit again all these populations that thought they had it under control, because it all depends on how much immunity do you get once you're infected. And we simply do not know that at this point. So I would say a second wave is nearly guaranteed, just because also there will be those that note this graph, this most likely scenario graph. Look at the blue line, the blue curve. It doesn't actually go to zero.
Right.
So there are still susceptible people in the population. So people that were never infected. The bigger the B value, the less that is, right? Because you come up here to this one, worst case, and you see that's a lower value in worst case. because you get more people infected. So I would say, yes, the second wave is most likely going to happen. Epidemiologically speaking, and all the models I studied while also in graduate school, everything I studied in graduate school about epidemiology and beyond, once I got out of school, I would say, yes, it is nearly guaranteed to have a second wave. And yes, it will most likely be in the fall. The reason being is we're going to get secondary waves from other countries that are now getting infected.
Right.
So if you look at the spread in Texas, you can see this is very geographic. It's very geographic. It has a lot to do with transportation and how people move around. So in Austin, when they were saying, oh, hey, our new cases are starting to level off, our new cases were going up. So to get this idea that you can think of this in terms of, hey, it's the whole state now, we're doing good as a whole state, is completely inaccurate on an epidemiological model. It's like, that's just not true. It takes time for it to start to spread. And the problem is people don't see it spreading fast at first.
Mm-hmm.
They don't understand exponential growth.
Right.
And they don't understand the rate of change of exponential functions, because everyone in this class knows the rate of change of an exponential function is exponential. Okay? So it grows faster. It grows much faster as time goes on. Right? It starts out looking, hey, this isn't that big of a deal. And then in 10 days, you go from 9,000 to 32,000 people.
Right.
So it's going to happen. And yes, at that point, you'd have to kick in the model again. But if the pandemic runs its course, you can actually then calculate the B value. Then you don't have to keep trying to estimate it because the pandemic already ran through.
Right.
Now, you're still going to want to keep checking it with actual data if a new wave hits, or it's like the flu and we get this every year.
Mm-hmm.
That's why the vaccine is necessary. But you would still want to compare it against data because you may have to adjust it slightly here and there. But you should be able to analytically calculate the B value once the pandemic has run its course.
A more accurate predictor, and you are in a better position for making decisions for the college and the community and so forth.
Exactly.
Right.
Exactly.
But I think from what we've learned from what you've presented, at least we can translate that into our personal decisions and decisions for our family and how we interact in the community. And I think that what you presented here is incredibly valuable. And this has been a tremendous blessing. I just want to say thank you, Mr. Witherspoon, for showing us your model. I think we have all learned something today. We've been able to see how what we've learned this semester, you have taken to another level. And it's amazing to see how you take your knowledge and you apply it to something that is very real and affecting every one of us. And you've turned it into this amazing model and information that we can consult to make important decisions. And you've reminded me of how much I love being a student. It's been a blessing to sit here and listen to you teach. And I've learned new things, and I know that my students have learned new things. And you're a blessing to our college. You've been a blessing to our class. I just want to thank you so much for your time today, your expertise. And to all of my students, are there any questions or thoughts? Okay, well, for respect of time, I think we will adjourn for the day. So again, thank you, Mr. Witherspoon. I'm going to save this video, and if with your permission, put it on YouTube and share it with the department, because I think it is fascinating. I think a lot of people will be really interested in this. So thank you.
All right.
Thank you so very much. We appreciate you a lot.
You're welcome. All right. See you all later.
Okay, bye-bye.